these guys, fundamental types of crystalline solids. And some of these we've gone over before. We can have molecular solids. They have individual units that are molecules. They generally have low melting points. Why do molecular solids have low melting points? The intermolecular forces between those molecules are relatively weak because you've got molecules. Then we have ionic solids composed of ions, cations and anions. They have high melting points. Why? Yeah, actually they don't technically have intermolecular forces. They have ionic bonds that go throughout the whole crystal. So an ionic bond is very, very strong, and so that's why they generally have very high melting points, because it's cation, anion, all the way through, and it's this attractions between full charges. Then we also have atomic solids, which are composed of atoms. Those are divided up into non-bonding atomic solids. Atoms only have dispersion forces, the weakest intermolecular force. So the non-bonding atomic solids are held together by dispersion forces. These are going to have low melting points, like really low melting points. Then you have metallic solids, atomic solids. These are held together by metallic bonds. What was the analogy we used for metallic bonds? The electron C. That each of these metal atoms lets a couple of electrons go, and we've got this pool or sea of electrons that's free to move around all these metal ions, and that's what holds the metal together. So that's going to be relatively strong, but metals have variable melting points. Some of them have very high melting points. Don't know why. My kids were talking about iridium last night. Iridium's a really cool metal. It's very unreactive. You can get iridium rings, but they cost like $4,000, Zach says. But, Zach would know because he just knows stuff. The reason they're so expensive is not that the metal itself is so expensive, although, it's a precious, expensive metal. It has such a high temperature, a high melting point, that in order to make the ring and size the ring, you have to heat it up to tremendous temperatures, and so the labor involved in that is crazy expensive. Other things like mercury is a liquid at room temperature. Gallium will melt in your hand just from the heat of your hand. So the melting points for those guys are variable. And then the next one is a network covalent atomic solid. And this is where the atoms are held together by covalent bonds. There are not a lot of these, but there are some. And these have high melting points. Quartz is an interesting substance, silicon dioxide, and you may say, yeah, but that's a compound, isn't it? But the individual atoms in here are not in discrete molecules. There are silicon atoms and oxygen atoms. The ratio is 1 silicon to 2 oxygens, but they are actually covalently bonded together all throughout the solid. I think diamonds are a much easier network solid to understand. A diamond is pure carbon. Carbon atoms, but they're covalently bonded to each other in this big lattice structure. Covalent bonds are strong, and so network solids have high melting points. Now I probably said all of this stuff. Oh well. Yeah, I said pretty much that. Ionic solids. Ionic solids form crystalline solids, and their coordination number represents the number of close cation-anion interactions. The higher the coordination number, the lower the potential energy, and the stronger it is. The crystal structure that we see in ionic solids is going to be a balance between coordination number, charge neutrality, and different ion sizes. Because when you have an ionic compound, you don't have all of the balls being the same size. In sodium chloride, chloride is large and sodium is small. And so when those pack together, they're going to pack differently than if you have all atoms of the same size. Here's cesium chloride. The cesium ion is smaller than the chloride ion, but they are similar in size. There's not a big difference here. And so it's going to form this simple cubic structure with the cesium ion in the center, coordination number of 8. Calcium sulfide does a similar thing. When the ions are different sizes, like in sodium chloride, the fact that we need charge neutrality is going to limit the ratio. We have to have 1 sodium for every chloride ion. And so that limits the coordination number to 6. You can't get a coordination number of 8. So this is going to be face-centered cubic with the chlorine. So if you look at this, this is the chloride in the middle with the 4 corners being the, gosh, my words are just failing me today. If we look at the green balls, that's a face-centered cubic structure. And then the sodium ions are small and they just fit into the holes in between. So in this cubic structure, we're going to have a unit cell that has 4 of each of the ions. It's going to have 4 chlorides and 4 of the sodiums. And that's the structure that sodium chloride has in rock salt. When you look at the little salt crystals in your salt shaker on the table, they look like little tiny cubes, don't they? That's what they want to do. They make little tiny cubes. The people that manufacture the salt, Morton, they don't do anything special to make them all come out so pretty and nice. There's no mold that they're making salt into. It just does that. When you get larger ions, a larger size difference, then you get some more complicated things. This is known as zinc blend. It's zinc sulfide. And here we've got sulfur ions and zinc ions. The sulfide ions do a face-centered cubic structure, and then the zinc are in these tetrahedral holes in between. What's a tetrahedral hole? Well, we've got these 4 sulfide ions, and the 4 of them form a tetrahedron. In the middle of that tetrahedron is a hole. So we call it a tetrahedral hole. And that's where the zinc's going to fit in. What if you have unequal numbers of cations and anions because of the charges? Calcium fluoride, you've got 1 calcium and 2 fluorides. Well, then things get a little more complicated. So here the calcium ions are doing a face-centered cubic structure, and now we've got the fluoride in all of the tetrahedral holes. So let's go back here a minute. Here we have an equal number of sulfide and zinc in the whole thing, not in this picture, but you have a 1-to-1 ratio. So the zinc is not occupying all of the tetrahedral holes, only half of them. Over here, where we have a 1-to-2 ratio, the fluoride's going to be in all of them. Again, the atomic solids held together by dispersion forces. These are going to use closest packed structures They don't have to worry about different sizes of atoms. All the atoms are the same size. They don't have to worry about charge ratios or anything like that. Low melting points because of the weak forces that hold them together. And the metallic solids, again, they're going to form closest packed structures because they have the same, they only have one kind of particle. And the melting points will vary. They just have varying bond strengths of those metallic bonds. Here's looking at two different forms of carbon. Carbon forms different network solids. Here's a diamond. And in the diamond we see a more three-dimensional arrangement where there's actually, so here's a layer, and here's a layer, and here's a layer, and there are actually covalent bonds between the layers. In graphite, we see the carbons with covalent bonds to each other, but in this layer, the bottom layer, they're bonded to each other, but there are no covalent bonds between this layer and the next layer. There are just dispersion forces holding those two layers together. What's one characteristic of graphite? It's slippery, right? You can use graphite to lubricate things. And it's slippery because the layers will slide against each other. Because they're not bonded to each other, they just have these weak dispersion forces. They're going to stay together, they're not just going to fly apart, but if you move this one, it can slide relative to that one pretty easily. So graphite has layers, and a diamond crystal is actually one ginormous molecule, all covalently bonded together. These are not forming closest packed structures. These are forming bonds. You can kind of see it in here. They're forming six-membered rings, and that has to do with the bond angles that carbon forms. So the structures are limited because of the bond angles. So they're not going to pack in like the other atomic solids do. Silicates are cool. So quartz is silicate, and sand is mostly silicate, and common glass is a form of silicate. So about 90% of the Earth's crust. These things have very high melting points. Well, not very high, high melting points. And so this, I think here they're showing us, okay, honestly, I'm not sure what they're showing us over there. Let's look at this one. This one's crystalline, okay? Here we're looking down the middle, and you could also look down the middle over here. There's an order. We've got, I believe this is the silicon, and this is the oxygen. Silicon, oxygen, silicon, oxygen, silicon, oxygen. There are not discrete molecules. This is why it's called an atomic solid as opposed to a molecular solid. They're all bonded to each other in an orderly pattern. Glass is an amorphous form of silicate, meaning it does not have a regular repeating structure. It can be argued that glass is actually a very, very viscous liquid. If you look at windows from very old buildings, like ones from the 1700s, and if you measure the thickness of the glass at the top of the window and the thickness of the glass at the bottom of the window, the glass is thicker at the bottom. It was not made that way. But over hundreds of years, the glass is slowly running down. The ripples in glass have to do with how it was formed But the fact that you can have ripples is because it's amorphous. There are many, many different kinds of glass. They'll put different substances into the glass and can change its characteristics. Some glass breaks very, very easily. Then there's safety glass that doesn't break as easily, and when it does, it breaks into little tiny chunks instead of breaking into large slivers that can really hurt you badly. Now, the stuff that we've got in lab here tends to break into nice, sharp pieces, doesn't it? Thankfully, nobody's gotten hurt. But glass is amorphous, but there are many silicates that are crystalline as well.